Even though molarity is often the most appropriate measurement for chemistry, many other fields and applications will use different concentration units, some of which are shown here. Before we talk about any units, notice that every concentration unit is a comparison of a measurement for the solute over a measurement for the solution. What unit is used and the scaling are the only things that change. For example, mass percent, mass of solute over the mass of solution, shown in the top left, is typically a measurement that's widely applicable since the masses don't change with temperature and we'll always get the same result. However, the volume of a solution is often more convenient to measure since we can calibrate equipment to deliver volume exactly, something that is impossible to do on a mass basis. If we use water at room temperature as the solvent, the mass in grams is almost equal to the volume in milliliters. So mass volume percents, mass of solute over the volume of the solution, and the left middle, is always in grams per milliliter. Fortunately, if you're mindful of units for the solution versus units of the solute, it's fairly easy to convert between these units using densities and molecular weights as appropriate. For example, if we wanted to convert the mass of a solution to the volume of solution in the denominator, all we need to do is multiply by the density of a solution. Mass percent and mass volume percent, the top two on the left, are both commonly used when the solute is originally solid, since it's easy to measure mass for a solid. But volume percent is preferred when the solute is liquid. For example, fizzy downer drinks are often reported with a percent ABV, which stands for percent alcohol by volume, as ethanol is a liquid at room temperature and atmospheric pressure, and so is water. Of course, we've already talked about molarity, which is the middle right, which directly relates to the number of particles and is more useful in chemistry. It's common to use metric prefixes to get molarity units to an appropriate scale. For example, lanthanides are often concentrated in seawater on the order of picomolar concentrations. Since pico means 10 to the negative 12th, picomolar would be 10 to the negative 12th moles per liter. You can't do the same thing with percents. Pico percent has no understood meaning. So instead of using percents, which literally means per 100, we use per something else to make the scale appropriate. Two such units are shown at the bottom. The most common units of this type in chemistry are parts per million, ppm, literally how much mass out of a million mass units, and parts per billion, ppb, literally how much mass out of a billion mass units. Parts per thousand and parts per trillion are often used as well, but since both would be ppt, we generally spell out the entire unit to avoid any confusion. These units are often used when a measurement, rather than a reactivity, is what's most important. Contaminant reporting is a great example. People talk about lead concentrations in parts per billion because people are looking at regulatory guidelines rather than expecting a particular reaction where the ratio of molecules needs to be understood. So parts per million or parts per billion are more appropriate in that context than molarity. To try to nail home the idea of parts per anything, let's walk through an example problem. Suppose I have soil in my backyard that has a dry composition of 70% clay and 30% sand. I also have it tested for lead, Pb, and it has a 0.00005% lead concentration. Typically, clay is a complex mineral composite, so the lead is part of the clay, and our percents really do add up to 100%. The clay and the sand make sense to express as percents, but the lead would never actually be expressed as a percent. The number doesn't make any sense to report with that low of a value. A percent is easy to convert to another unit as long as you think of it as simply defining the solution spaces, how much solution we actually have. So 1% is saying that the mass of the solution is 100 grams, and the mass of the solute is just 1. If you divide a percent by 100%, or by 100, you go back to the decimal basis of the number, essentially just parts per part. If we want to go from parts per part back to parts per billion, we just say that we want a billion parts now, and so we'll multiply by 1 billion. So 0.00005% is the same as 500 parts per part, or per billion parts, or 500 parts per billion. The overall strategy for converting between percent and other per units is to get them back to the decimal basis when it's percent by dividing it by 100, or if it's parts per billion by dividing it by a billion, and then multiply by your new basis, whether it's parts per million but multiplied by a million or percent multiplied by 100. In fact, every conversion between units will be easiest if we convert to the decimal basis. Let's walk through a few more of these conversions. Suppose we have a mass percent solution. If we divide by 100 to get it as a decimal, which is usually the best first step, every conversion is some combination of using density and molecular weight as conversion factors. These are relatively straightforward dimensional analysis problems. If we want to convert to mass volume percent, the top unit can stay the same, grams solute, but the bottom unit needs to change from grams solution to milliliters of solution. Note that we're specifically noting which units go with solute and which units go with solution. This conversion is easily accomplished by multiplying grams of solution over milliliters of solution, which is the solution density. If we want to go the opposite direction, it just requires flipping the conversion factor, dividing by density or multiplying by its inverse instead. If we want to convert mass percent to volume percent, we need to make two density-based conversions. The first gives us mass volume percent, like we just did, and the second uses the density of the solute instead, and it converts to volume percent. Do you need to multiply or divide by the solute density to go from mass volume percent to volume percent? Looking carefully at the units should show that grams solute needs to be on bottom and milliliter solute needs to be on top. Dividing by the density of solute is what we actually need to do. Don't memorize these conversions. Instead, be careful when you're writing your units to keep track of not just the unit, grams, milliliters, or moles, but also the thing that's being measured, solute or solvent. For example, grams sodium chloride, milliliters of solution, etc. If you apply units carefully in this way, all of these problems are just dimensional analysis with densities and molecular weights as conversion factors. If we want to now go from mass percent to molarity, that also involves going through volume percent. The top needs to be converted between grams and moles of solution in this instance, which is essentially dividing by the molecular weight of the solute, and then converting the milliliters to liters, which is a simple metric conversion. Of course, every one of these steps can be reversed. The point isn't to memorize each conversion, but instead to see how carefully labeled units can be related by simple conversions. On this page, there are some commonly encountered measurements with different units. Pause to try each conversion, and we'll walk through each together afterward. The percentage on milk is actually the mass percent for fat in the milk solution. Nobody I know actually masses out their serving of milk, so let's convert that mass percent to a mass volume percent. Give it a shot. 2% as a decimal is 0.02 grams of fat per gram of milk. We get that by dividing 2% by 100. We need to convert the grams of milk that are on the bottom to milliliters of milk in the bottom in the product unit, which we can do by multiplying by the given density in grams per milliliter of milk. Our product is 0.02 grams of fat per milliliter milk, or 2% mass per volume, or mass to volume. For most water-based solutions of moderate concentration at room temperature, the mass percent and mass volume percent are the same to about 2 significant figures. Our next problem is blood salinity. Doctors and nurses will administer isotonic saline solutions, solutions with the same salt concentration as blood, as 0.9% mass to volume sodium chloride. Chemists and biologists care about nerve cell action potentials, which are based on molar concentration, so give it a go. Try to convert that to molarity. It's helpful to think about our target as actual moles of salt per liter of blood, so we can always see what direction we need to go. Since we start out with 0.009 grams, that is 0.9% over 100, of sodium chloride per milliliter blood, we know that we can convert the milliliters to liters with a metric conversion and the gram sodium chloride to mole sodium chloride with molecular weight. The units guide our setup, so we multiply by milliliters over liters and divide by molecular weight. We end up with a fairly small number, 0.0002 molar sodium chloride. We might choose to express this instead as 200 micromolar sodium chloride. Notice that we didn't actually need to use the blood density here. Its units of grams blood per milliliter blood were not actually useful to us. Again, on the blood theme, blood glucose meters use a concentration measurement of milligrams per deciliter. If we had only memorized how to convert between units, bizarre units like this would throw us for a real loop. But if we are carefully labeling units in order to solve the problems, we won't have an issue at all. The strategy is still the same, so give it a go. The first conversion is to mass volume percent, which has units of grams per milliliter. This is a set of two straight metric conversions, milligrams to grams, and then deciliters to milliliter. The product is 0.00070 grams of glucose per milliliter blood, or a 0.070% mass volume solution. From grams per milliliter, we can easily convert to moles using molecular weight and liters, and to liters with a metric conversion for a final value of 0.0039 molar. Our final question is about low carbon steel, the most common type of structural steel. It's reported as a mass percent, but the value is low, so a part per million may make more sense. That is, if engineers weren't labeling it. So let's convert to parts per million. Percent needs to be divided by 100 to convert to a decimal, essentially parts per part, and then multiplied by a million to get parts per million. The result is 2,500 parts per million, which is actually pretty high to report as parts per million. With apologies to engineers everywhere, we'll acknowledge 0.25% as a better way of representing this concentration.